Okay, so this is going to be a video on the review for Chapter 5. Alright, so find the extreme values of the function on the interval and where they occur. So, extreme values will occur when f prime of x is equal to 0 or undefined, or endpoints. So here. So, we're gonna use what's called the, if you guys remember, it's called the candidates test. So we're gonna try and find critical points first, and then we'll use endpoints as well, and then we're gonna use the candidates test to find the extreme values. So, g prime of x, g of x in this case is negative 2, x to the negative 2. So drop the power, that's going to be equal to 4 over x to the third. And I'm going to set that equal to 0. Now, this derivative will never equal 0, so this expression right here will never actually equal 0, because the only way for this expression to be 0, the only way for a rational expression to be equal to 0 is if the numerator is equal to 0, but since the numerator is 4, then therefore it will never equal 0. So, but it will be undefined when x is equal to 0. The thing about that, though, is that 0 is not within our interval, so it's irrelevant. So our interval is from 1/2 to 2, and nowhere in this interval does the derivative equal 0, and nowhere in this interval is the slope undefined. So that means if the derivative is never 0, that means it never changes from increasing to decreasing. It's just going to stay increasing or stay decreasing. So either so if you think about it, from 1/2 to 2, the function is either always going down or always going up. And so, yeah. So we're just going to use the candidates test. So, and the only thing that we have to use for the candidates test are the endpoints. So if we plug them in, so if we plug in 1/2, negative 2 over 1/2 squared is equal to negative 2 over 1/4, which is equal to negative 2 times by 4, which is equal to negative 8. Yep, so negative 8 for that one. And then now we plug in 2, so we get negative 2 over 2 squared. That's negative 2 over 4, which is equal to negative 1/2. So negative 1/2 right there. So for this one right here, we know that the minimum is equal to negative 8 at x equals 1/2. Maximum is equal to negative 1/2 at x equals 2. We can go ahead and try and verify that here if we want to graph the function. So the function being negative 2 divided by x to the x squared. Oh man, if I can remember now, we'll do 0.5 less than, let's do less than or equal to x, which is less than or equal to 2. So here's the interval. Kind of see that. Yep, there you go. 0.5 is negative 8, that's the minimum. Maximum 2 at negative 0.5. So, okay, there you go. I do believe the key is wrong. That's because the key, I switched out the question. So, alright, for 2, find the extreme values of the function where they occur. So, similar problem, except not over a given interval. It's just the domain of the function. So, we don't have endpoints to test. We're just going to, I'm just going to use the first derivative test. So, we're going to need the derivative. So, y prime will be equal to, I'm going to need the quotient rule. So, low d high minus high d low, which would be 2x, and square the bottom. Okay, so this is the derivative. I'm not gonna, I guess I could, but I'm not really gonna bother simplifying right now, because all that matters is we're trying to find when the derivative is equal to 0, because that's where extreme values occur. Or when the denominator, or whenever it's undefined. So the thing about, I don't think that the derivative, this expression, the derivative, is never going to be undefined, because the denominator will never be equal to 0. X squared will always be 0 or positive, and so because of that, this part right here can never equal -1, and if this never equals -1, this never equals 0, and therefore the denominator never equals 0. And so really all that matters is the numerator. So in the numerator we have 5x squared plus 5 minus 10x squared, which is equal to negative 5x squared plus 5. And remember, we're going to set that equal to 0. And let's see, I'm going to factor that. I can pull out a negative 5, and I'm going to get x squared minus 1. And that's factorable by x plus 1 and x minus 1. So x will be equal to -1, and x will be equal to positive 1 as the solutions to that right there. Which means that that's whenever this will be equal to 0. So I'm going to use a number line, the first derivative test, and we got -1, we got 1, and we'll test some points into the first derivative. So let's say we plug in 0, so let's do y of 0. Sorry, y prime. We want y prime of 0. We're going to plug it into the derivative. So if we plug that in here, yeah, let me simplify this just a little bit. So this expression, remember that we simplified the numerator. This numerator is equal to negative 5x squared plus 5 over x squared plus 1 squared. Okay, so if I plug 0 into the derivative, that goes away, so we're left with positive 5. Remember, the denominator is always positive, so this doesn't really matter, it's always positive. So, but if we plug in 0, that goes away, so we get positive divided by positive, so we're going to be positive here. Let's check something over here, so like y prime of 2 or something like that. So if I plug in 2, this right here would become 4, that would become negative 20, and negative 20 plus 5 would still be negative, so negative divided by positive, so this will be a negative. And let's just make sure that over here we check over here. Let's try y of negative 2. That really won't change anything, because negative 2 squared will be 4. 4 times negative 5 will be negative 20, so the result is the same. So will be negative here. So here, the function, so this function y is going to be decreasing, then it's going to have to change to increasing, and decreasing again, because slope here is negative, so the function has to be decreasing. We know the slope here is 0, so it has to have a horizontal tangent, and then it's going to be increasing. Again, it's going to have a horizontal tangent here, because at 1 it's going to be equal to 0, and then it's going to be decreasing positive. So we have a minimum here and a maximum here. So here So minimum at x equals -1, maximum at x equals 1, and we'll have to plug these in to find the extreme values. This is just where they're happening at. So if I plug -1 in here, so if we plug in -1, we'll get -5 over, and then if that's -1 squared, that's going to be -5 over 2. So, so minimum is -5/2, and then if I plug in 1, I'll get 5/2. So this will be 5/2. Okay. I think that's everything. So, okay. The mean value theorem can be applied to which of the following functions on the closed interval from -5 to 5? The mean value theorem says that a function f is continuous and differentiable on a closed interval from a to b. So if a function is continuous and differentiable on a closed interval from a to b, then at some point in that interval, then at, we'll say c, which is an element of the interval from a to b. So c is just some x value in between a and b. So then at c, which is an element from the interval from a to b, it's just fancy language right here. Yeah. Then at this value right here, f prime of c will be equal to the average rate of change. So that's going to be f of b minus f of a over b minus a. So, considering that has to be continuous and differentiable, if we take a look at these right here, well, take a look at a. A is not continuous at 0 because when sine is equal to 0, this will be undefined. So in 0 is within the interval from -5 to 5, so it can't be a. Here, this denominator cannot be equal to 0, and it would be equal to 0 at x equals 2 or -2, which would be a problem here. This right here, x cannot be equal to 1, and this right here, this would be equal to 0 from, so this would be undefined when the denominator is equal to 0, which happens at 6 or -6, but that is outside of the interval. So therefore, it has to be b. So it can, the mean value theorem would apply to this one right here. Okay. The function g is shown in the figure. The function g shown in the figure is continuous on the closed interval from x equals 0 to x equals x sub 6. And it's differentiable on the open interval, so it's differentiable in between those 2 points, where x1 through x6 are points on the x-axis. Based on the graph, what are all values of x that satisfy the conclusion of the mean value theorem applied to g on the closed interval? So remember just this definition of the mean value theorem. So this slope right here, this is the slope of this graph right here. The slope of this line segment right here would be the average rate of change from 0 to 6, which means at some point in this interval right here, there has to exist a value where the slope at these points, so you can see the individual slopes at these points, at some point it's guaranteed that there is a point where the slopes at a specific point would be equal to the slope of the secant line, which is the average rate of change. So you can see that with this right here, with the secant line, there are actually 2 points in this interval for which it appears to be parallel, which means that at this point right here, so what point is that? Is that x sub 5? And right here it's x sub 1. So x1 and x5 would be the point. So let's see, based on what are the values of x that satisfy the conclusion? x1 and x5. So x1, x5, sure, that would work right there. Okay. Whoops, sorry. So find the value or values of c that satisfy this right here is the mean value theorem for the function here on this interval. So I'm going to get rid of this definition that I wrote right here. So find the values of c that satisfy this right here. So I'm going to find the average rate of change using this interval right here. So f of 1 minus f of negative 2 over 1 minus negative 2. So f of 1 would be equal to 1 plus 5 plus 2, which would be equal to 8, minus f of negative 2. So if I plug in negative 2, that's going to be 4 minus 10 plus 2, which is going to be 6 minus 10, which would be equal to negative 4. Okay, over 1 plus 2. So we're going to have 12 over 3, which is going to be equal to 4. So that's the average rate of change. Now I'm going to find the derivative here, f prime. So f prime of x would be equal to 2x plus 5. And I'm going to set the derivative equal to 4. And if I solve this expression for x, I'm finding the value of c right there, which is what I want to do. So 2x is equal to, if I subtract 5, I'm going to get negative 1, and then I'll divide by 2. So x will be equal to negative 1/2. So x equals negative 1/2. This is the value in this interval right here where the average rate of change will be equal to the derivative of the function. So there you go. Okay, kind of trying to decide if I want to stop the video there because I don't like videos going too long. So I think I will, and I'll finish the next page or two in another video.